Right, here we've got a setup where there's a hydroelectric plant. Generates electricity is transferred along the lines through a transformer to the town. So into the starter lines is 50,000 volts RMS AC, and the power lines have some resistance and they use some of that voltage up. So there's only 49,400 left over when you get to the transformers. The first question is asking the power supply to the transmission lines. It's a pretty easy one to start off with. Formula for power is voltage times I. So this is really the total power. So the total voltage is, we've got all these voltages to choose from, but we're looking at the total voltage supplied to the lines, 50,000 volts. And the current they've given us as well, 15 RMS. Now, a common mistake in this is people see the RMS and they start timesing by √2. We want to use this RMS for doing these calculations. It's like the average voltage, the average current, we want to use it for this. So no times or divide by √2 here. Just straight use these. Okay, so 50,000 and the current, what's that again? 15 amps. Times those together, 5 is 750,000 watts. You could also put that as 750 kilowatts. You could also put that as 7.5 by 10 to the 5 watts. Any answer is correct. 7.5 by 10 to the 5. Alright. Oh, wrong one. Some townspeople are concerned about the high voltages, and they propose the same power could be transmitted more safely at a lower transmission voltage. Explain clearly why this proposal would increase the power losses in the transmission process. Right, this is 3 marks, so we want 3 dot points here. So the same power at a lower voltage. I'll start this one because power equals VI. If voltage is decreased, then if that goes down, for this to be the same, I must go up. Then the transmission current must be increased. But the power loss, I need 2 S's. The power loss in transmission lines, power loss equals, you should know this one, I squared R. So, last dot point, if I is increased, that goes up, that will also go up. The power loss in transmission lines would increase. Alright, the proposal is not accepted. The transmission lines operate as originally designed. With the current of this, the total power loss, P loss, in the transmission lines is 9,000 watts. Calculate the resistance. So we can use that same formula there. P loss equals I squared R. We're trying to find R. So we want R by itself. We have to divide by I squared. Divide both sides by I squared. And we get P loss over I squared equals R. Put the numbers in. 9,000 divided by 15 squared equals R, and that is 9,000 divided by 15 squared is 225, and you get 40. 40 ohms. Alright, on the edge of town, a transformer is used, this was in the picture, to transfer the voltage to 250 RMS from the 4000 voltage. So this is the V secondary, and this is the V primary. This question is asking us to calculate the value of, or really the ratio, this is what it's asking, of the current, I'm just going to write it as this, the current in the secondaries over the current in the primaries. Now if we go from 4940 to 250, our voltage gets smaller by, if you do the calculation of 4940 over 250, I think you get 198. So this gets smaller by 198 times. If our voltage got smaller by that amount of times, our current has to increase by 198 times. So this secondary is bigger than our primary by 198 times. And that's what this is asking us. It's asking us how much bigger is the current in the secondary than the current in the primary. This is what this ratio means. And so, to do our working for that, we've done it here, the answer is 198. But just to make sure we've got our working, the ratio of the current from the secondary to primary is equal to the ratio of the voltages from the primary to the secondary, because one goes down as the other goes up, and we've worked that out already, which was 198.